find quarks and gluons with a common name, partons. I'll say a few words about similarities and differences with respect to the more famous electromagnetic plasma and with the quark-gluon plasma in the early universe. Also, I'll say something about phase diagram of nuclear matter. Most of the talk, I'll present some of our results that are connected with collective anisotropies, initial state fluctuations, and jets inside the quark-gluon plasma. So both quark-gluon plasma and electromagnetic plasma, they are built from basic constituents. In the case of QGP, these are quarks and gluons, and in the case of electromagnetic plasma, these are electrons and ions. But the strength of the interaction between these two is drastically different. And at the transverse momentum of 1 GeV, it is about, the difference is about of two order of magnitudes. Just due to that, we have a very fast thermalization, which happens in the quark-gluon plasma. And because of that, we are able to quantify it with some macroscopic quantities like temperature, pressure, viscosity, etc. Also, at the beginning, people believed so that QGP is kind of a weakly interacting gas of partons, but experimental studies shows that it is, in fact, a strongly coupled quantum chromodynamical system, which best description at high energies is given by relativistic hydrodynamics. Phase diagram of nuclear matter is presented in temperature and baryochemical potential mu b, and at high temperatures and small baryochemical potential, the number of baryons is close to the number of antibaryons, and that is a situation which is similar to the early universe. Lattice QCD calculations finds a crossover transition between hadronic and partonic matter. Generally, T mu b diagram contains the ordinary hadronic matter, which is separated by the phase transition from the QCD system. At smaller temperatures and high mu b, that corresponds to the densities of neutron star cores, some model predicts some exotic objects like quark stars and some exotic phases like color superconductivity. One of the earliest phases of the universe was in the form of quark-gluon plasma. It appeared about 1 microsecond after the Big Bang and lasts for about 10 microseconds when the universe became large and cold enough that confinement of partons took place. I find it very interesting that the universe in the QGP phase was in fact a liquid. Even more, the most perfect liquid with the smallest shear viscosity to entropy density ratio. Yesterday, Damir Devetak presented some, up to now, probably most precise results about measuring of shear viscosity. And it is, let's say, roughly about 0.2, which is for 1 order of magnitude smaller than in the case of water. This is concluded based on the fact that the relativistic viscous hydrodynamics gives the best description of the QGP. In the relativistic nuclear collisions, after the initial state where the fluctuations in position of nucleons, overlapping nucleons, and even in position of partons within nucleons, take a significant role for further evolution of the collision. So then we have appearance of the quark-gluon plasma that exists quite shortly. It is up to 10 Fermi over C, which is 10 to the minus 23 seconds. When such QGP expands further and cools down, the system confined back into hadronic matter, part of which we can detect. 40 years ago, first fixed target experiments appeared at GSI in Darmstadt in Germany and Beverlak in USA with colliding energies of few GeV. They were able to produce pions and kaons. A decade later, first fixed target experiments with a collision energy of one order of magnitude higher managed to produce plenty of pions, kaons, lambdas, newly produced protons, and corresponding antiparticles. 20 years ago, relativistic heavy ion collider in Brookhaven, RIC, realized first heavy ion collisions at 200 GeV per nucleon. They also announced first creation of the quark-gluon plasma in such collisions. Finally, 10 years ago, Large Hadron Collider, LHC in CERN, made collisions with energy of few TeV. Today, there is again an interest in nuclear collisions at lower energies where we believe that we'll find even more rich physics. Accelerators NICA in Dubna, CBM at GSI in Darmstadt, and JPAC in Tokai in Japan are under construction. Here are shown some existing experiments like NA61 at the Superproton Synchrotron, SPS, in CERN, then LHCb, Atlas, ALICE, and CMS at the LHC in CERN. Also at RIC there is STAR, Phoenix, Phobos, Brahms. NICA Collider in Dubna is under construction, as well as FAIR in GSI with a few experiments, and JPAC heavy ion program in Japan. There are also plans of building huge colliders like Future Circular Collider in CERN and Circular Electron Positron Collider, CPC, in China. There are several probes listed here using which one can study relativistic nuclear collisions and possible formation of the quark-gluon plasma. Experimentalists from Serbia are mainly involved in studying collective phenomena, initial state fluctuations, and jet quenching in the dense and hot QGP medium. Recently, we, together with China, we founded Strong Coupling Physics International Research Laboratory, and we are planning to work not only at high LHC energies, but also at lower energy collisions within NICA and JPAC experiments. There are many theoretical models which attempt so to describe the evolution of the relativistic nuclear collisions and possibly formed quark-gluon plasma. They are divided into three main groups. One is based on hadronic cascade, and mainly it describes collisions at lower collision energies. Another one are hydrodynamical models, and they are used for high energy nuclear collisions, and they are also hybrid models. By studying different observables, it is possible to make distinction between different models. Our focal point of our group is investigation of collective anisotropies. They arise from the pressure difference in pressure gradient in plane and out of plane of the overlapping zone in the collision. So, and they can be characterized by Fourier harmonics, Vn. There are several methods which have been developed to enable studying of anisotropies, like event plane method, scalar product method, method of two particle correlations, method of cumulants, which involve the many particle correlations, and Liang zero method, principal component analysis. Each of them has some advantages and some disadvantages. 10 years ago, it has been realized that the initial state fluctuations have a significant influence on nuclear collisions, and that they are responsible for appearance of higher order collective anisotropies. Namely, in a simple cycle-like geometry, one could expect the appearance only of the elliptic flow. So if we would have a smooth energy density distributions and perfect cycle-like geometry, but that is not the case. So then we have appearance of higher order harmonics, and it is especially important in ultracentral collisions, where one in that simplified picture would expect zero anisotropy. Also, they are quite important in highly asymmetric proton-lead collisions, and even in proton-proton collisions, because of fluctuations in the position of partons, one can expect also huge influence of the initial state fluctuations there. And even in proton-proton collision, one can expect appearance of a small drop of the QGP. In order to make you more familiar with what and how we are investigating the QGP, I'll show some of our results. And I'll start with an anisotropy measured at Ceres Na45 experiment at superproton synchrotron in CERN, and it is a fixed target experiment. So here are shown results for the elliptic flow, V2, of charged pions, K0 short mesons, and also baryons, so lambda baryons. And out of them, we were able to extract statistically the elliptic flow of protons, which is also baryon type. Here you can also see some thermodynamical, hydrodynamical predictions with two different freeze-out temperatures, and for mesons, they work rather well. For example, here, one can see that the system formed in more central collisions, such a system is bigger, and it can cool down longer and can reach lower freeze-out temperature. Freeze-out temperatures are somewhere ranged between 120 and 160 MeV. Yesterday, Damir, in his talk, showed so that now rather precisely measured the freeze-out temperature is about 137, but it is averaged over different centralities. For the first time at the SPS, we measured triangular anisotropy. It shows existence of E3, and it is a consequence of the initial state fluctuations. But the magnitude of the triangular flow is significantly lower with respect to such anisotropy measured at RHIC and at the LHC. My understanding is that going to smaller colliding energies, the initial state fluctuations became more and more smeared out, so that at even lower energies, we would expect a triangular flow which is quite close to zero, or zero at enough small energies. Now I'll show some results on jet suppression, or how we say jet quenching at the LHC from the ALICE experiment. It is also it is now a collider experiment. So one can define IAA observable as a ratio of jet yields in lead-lead and in PP collision at a given PT. Jet, it is a spray of particles, and it arises from the fragmentation of heavy quarks formed in the very early time of the collision of two nuclei. So here we can see a significant enhancement at all centralities and at low PT on both sides, so near and the away side. There is practically no suppression at the near side, which is expected, and it is explained by a short path travel of jets through that dense QGP medium. But on the other side, on the away side, we see a strong jet suppression, and we explain that with a long path travel of jets through the QGP. Sorry. Now I'll move to the anisotropies from the CMS at experiment at CERN. So first of all, I would like to say that CMS is able to extract really ultra-central collisions, 0 to 0.02% centrality. And here are shown Fourier harmonics of different orders in ultracentral lead-lead collisions measured using two-particle correlations. And one can see that all orders of Vn tend to saturate, approaching the highest centrality. The effect is entirely induced by the initial state fluctuations. Ultracentral collisions are in fact ideal testing grounds for the effects due to the initial state fluctuations. For example, this plot is quite intriguing, PT dependence, and it shows so that higher order harmonics dominate over the elliptic flow, which is not the case for other centralities. In pure hydrodynamics models that include fluctuating initial conditions, these distributions should be PT independent. So it is Vn power to the 1 over n divided with V2 power to the 1 over 2. So they include elliptic and higher order harmonics. So strictly speaking, it is not PT independent, but it's, let's say, fairly fulfilled in the low PT region, which is expected to be region where hydrodynamics works, because hydrodynamics works up to, let's say, depending on energy, but up to, let's say, 3 GeV, not for PT above that. The event plane is believed to be a global quantity. So the event plane is experimental quantity, which is kind of the best description of the so-called reaction plane. And the reaction plane in that ideal cycle-like geometry is a plane which is constructed from the beam direction and from the impact parameter vector. This is a vector which connects the centers of the colliding nuclei in the transverse plane. And we would have there only that elliptic symmetry. But again, due to the initial state fluctuations, it is not the case that the event plane is a global quantity, in sense so that it does not depend on PT or on pseudo-rapidity. Pseudo-rapidity is a variable which describes collision in longitudinal direction. This effect is, of course, very, very small, but with huge statistics collected by the CMS, and now new methods which are quite good and sensitive, we were able so to find out that really there is that PT dependence of the event plane. So here you can see, for example, Fourier decomposition, and that Pn in fact is not a global but depends on PT and pseudo rapidity. So as I told, so it appears because of the fact that the energy density distribution is not a smooth distribution in the overlapping region, but it is more like has that lumpy structure, which at the end, in fact, we can see from the final variables like PT, phi, eta, which we can measure in the experiment. More details about that was presented yesterday in Damer talk, because these are in principle able so to extract some quantities like viscosity, both bulk and shear viscosity. Now I'll speak about principal component analysis, a method which can reconstruct not only ordinary Fourier harmonics, which we are calling them now leading flow harmonics, but also additional sub-leading flow modes, which can be connected with the initial state fluctuations. These sub-leading flow modes, their signal is extremely, extremely small, for 3-4 orders of magnitude smaller with respect to the leading flow modes. So what is the method? So one can make a two-dimensional random Gaussian distribution and construct a matrix from variances and covariances out of it, then to diagonalize it and to solve to get eigenvalues. So in the experiment, we used two-particle Fourier harmonics where background has been subtracted to construct such a matrix to solve the eigenvalue problem, and then to get two-particle Fourier harmonics, but now also for different orders like leading and sub-leading. Next one is already too small so to be measured. And out of them, finally, to get a single particle anisotropies, but also of different orders like leading, sub-leading, and that was done also for elliptic and for triangular order in that ordinary ordering of Fourier decomposition. And here are shown results for the elliptic flow in lead-lead collision. So with blue markers are shown leading flow values, and they are in a good agreement with experimental measurements using another method, so two-particle correlations. But what is more interesting are these with these red symbols, which shows the subleading flow modes. We see that its magnitude increases with PT and with centrality. And generally, so we see a good agreement between experimental measurements with different, using different methods. Here are shown corresponding results, but now for the triangular flow. Again, we see a good agreement between experimental two-particle flow measurements and measurements performed using the principal component analysis. Again, we see also subleading flow mode, which correspond to the triangular flow, but now it is almost zero, which means so that the triangular flow is much better factorized than the elliptic flow. Here are shown the same results in the same colliding system and in the same energy, but obtained using the HyJet++ model. That model is a theoretical model based on relativistic hydrodynamics and jets. We see there is a rather good agreement between HyJet++ predictions, canceling leading flow mode, and the experimental measurement. But what is more interesting is that HyJet++ model predicts existence of the subleading flow with behavior which is rather similar to the one seen in the experiment. Because this paper is published before the CMS paper, we couldn't plot on it the experimental CMS data. Here is shown the same, but again, in the case of triangular flow, and again, so we see so that that the subleading flow modes for the triangular flow from HyJet++ model is almost zero, which again means so that it factorizes much better than the elliptic flow. Beside the HyJet++ model, we were also using, to say, completely different model, AMPT model, a multi-phase transport, which is a hadronic cascade model, which is also prepared to be used also at high energies. And in some cases, it appeared to give a better predictions, for example, than HyJet++. So here are, for example, correlations between different harmonics like V2, V3, V2, V4, V3, V4 for different centralities. HyJet++ model didn't include quadruple eccentricity, and because of that, it completely fails in descriptions of V4 harmonics. Also, HyJet++ model was concentrated mainly on the central collisions, not at the peripheral collisions. But what we see here, comparing these two models, it seems like so that MPT model describes these correlations much better. Even it is able so to predict existence of this boomerang-like structure in peripheral collisions, which is also seen in the experimental one, but in the experiment, the opening angle is much larger than the one seen in the AMPT model. We also use the more demanding cumulant method to measure some very fine effects from anisotropies. For example, if the system behaves according to hydrodynamics, then the distributions V26 minus V28, so these 6, 8, 4, so these are different orders of cumulants. And all of them are connected with the elliptic flow, V2, V2, you see. So V26 minus V28 should be the same as V24 minus V26 divided with 11. So that predictions comes from the hydrodynamics. And here on this plot, we see the experimental ALICE data and the HyJet++ predictions, and they quite well agree with hydrodynamical predictions. Also, another prediction is that so how to say, elliptic flow, it does not have a sharp value, but it is distributed. You can find events with high V2 or with small V2 from the same, for example, centrality class. But the distribution of V2 is not Gaussian, symmetric Gaussian, but it is skewed. And according to hydrodynamics, the skewness should be negative. So here, experimental results and model predictions are showing that skewness is really negative, but HyJet++ predictions gives a much stronger magnitude with respect to the experimental measurement. So in conclusion, by measuring anisotropies experimentally and calculated from different models, we are trying to extract some quantities like temperature, viscosity to entropy density, and to check does this behaves like viscous relativistic fluid or not. Thank you for your attention.
It is time for questions. Do we have raise hand? Yes, Damir Devetak. Have a question?
Very nice talk. So just one question from my side and a small comment. So a lot of content, a lot of information, good information. So a few things were mentioned in the talk. Different signals, flow and jets, and then fluctuations, different methods. So perhaps the question on the methods, since you have to simply calculate flow and jets differently, is there a best method, for instance? On paper, is there a method that removes all the jets from the calculations? That's the first question. And perhaps the second one, just a small comment on fluctuations and how fluctuations affect the methods that you mentioned.
So answering first question, I remember some time ago, like 10 years ago or more, there was a smaller number of methods. Methods have been developed by some theoreticians. And when we were applying these methods on the experimental data, we saw that they do not give exactly the same results. And it was also kind of a puzzling. And so let's say like this: if there would be really complete isotropy, no any asymmetry, so then all these methods would give zero. If you would have that ideal cycle-like geometry with only elliptic flow inside, then I think that all these methods would give the same results. But in fact, we have these fluctuations, and these different methods are somehow sensitive. Some of them are more sensitive to the fluctuations, some of them are less sensitive. For example, here from this last plot, we could see so that higher order cumulants, in fact, are not equal as they would be in the case if there would be no fluctuations. But just because, but they behave somehow in a predictable way in the presence of the fluctuations, so they can somehow to study these fluctuations and the influence of the fluctuations on the anisotropy. And how was the second question? Sorry.
So on paper, what is the best method to remove jets, for instance? Because you have to calculate flow and you have jets as a signal. So on paper, because you mentioned a couple of methods, and
it's also a difficult question. So one rather simple method is, so if you do this two-particle, two-dimensional distribution, delta eta, delta phi, then you can see jets at delta eta, delta phi close to zero, and you can cut on delta eta to remove them because they are short-range correlations and azimuthal anisotropies are long-range correlations. You have still enough data so precisely to measure azimuthal anisotropy. But the problem is on the away side, because jets are there quite spread, and there could be some remnants still there. Theoretically, Liang zero method is claimed so to remove any kind of non-flow correlations. But the problem with that method is that you need some extremely huge statistics, which is not available. And you will get also, how you go to higher order, you will get bigger and bigger statistical errors. And that's also a problem.
Yes. So technical limitation at the end. Yes. Okay, nice.
Yeah.
Okay. Thank you.
Thank you.
If there are no other questions, we can thank to the Jovan for this very interesting lecture and go with the program. Thank you, Jovan.
Thank you.
Now it's my pleasure to introduce the next speaker, Professor Anđelka Kovačević from the University of Belgrade, Department of Astronomy, Faculty of Mathematics. She's expert in AGNs, astrophysics, and she will give the lecture about LSST and AGNs. And her investigation and team.
Thank you so very much. Good morning. Control room, I am in fully operable mode. Could you confirm your screens, please? Sasha, could you confirm that it's all okay with my presentation?
Yes, it is okay.
Ready to go. This is the story about the chasing electromagnetic counterparts of nanohertz gravitational wave sources with decadal optical survey called the Legacy Survey of Space and Time, or LSST, and potential contribution of the Serbian team within the LSST led by Professor Luka Popovic. And firstly, let us introduce LSST. At the bottom, you can see the LSST, the telescope mirror of the size of the tennis court, which will perform the LSST. LSST is astronomy's next discovery machine, with the first light the next year. With its 8-meter mirror, it won't be the largest telescope on the planet, but it will be by far the fastest instrument of this size. 3 times a week, its 3-gigapixel camera, the largest digital camera ever built, will map the entire visible sky. Dedicated algorithms will search through the staggering amount of data, some 20 terabytes per night. The data volume in astronomy doubles at Moore's law, reflecting the same law in technology, implying that LSST amount of data will comprise large hadron collider data. With LSST, astronomers will use large databases as virtual telescopes that are capable of seeing things that previous concept of telescopes cannot. On the face of it, telescopes and databases are not anymore very different things, and LSST will be fully integrated system of the machines, data, algorithms, and humans. LSST will revolutionize our understanding of billions of different objects across different dimensions. In all, the LSST will produce high-purity sample of at least tens millions well-defined, optically selected, actively accreting supermassive black holes. Einstein thought nature would protect us from the formation of black holes. However, to the contrary, nature makes them in abundance. The task of our Serbian group will be to investigate supermassive binary black holes in time dimension related to their variability and periodic oscillations in their decennial-long light curves. Most of what we know about supermassive black holes thus far has been informed by electromagnetic observations of active galactic nuclei over several epochs of cosmic evolution, about what you have already heard from the Professor Haga in Netzer's excellent talk yesterday. As all massive galaxies in the universe possess supermassive black hole in their center, active galactic nuclei, or AGN, are a fraction of these galaxies that have actively accreting supermassive black holes. Accretion results in luminous galactic nuclei that can outshine the light from the entire galaxy, and in many cases produces bipolar outflows that can span intergalactic scales. The most likely scenario for the production of such huge luminosity is the conversion of gravitational energy of matter accreted by the black hole to the mechanical and electromagnetic energy. The most efficient model for accretion is through the circular, geometrically thin, optically thick disk formed around the black hole, where the angular momentum is carried outwards as a result of the flow of matter inwards. The typical AGN is a far complex system made of at least several components, accretion disk where rapidly rotating gas in the gravitational field of the supermassive black holes form accretion disk, broadline region where the broad and optical lines originated, dimensions between 10 to 100 light dates, and very dirty place that is molecular torus, which is located within few parsecs from the supermassive black hole. And at the last narrow light region, which is located about 100 to 300 parsecs from the supermassive black hole, where the narrow optical lines are created. The basic taxonomy of AGN comprises type 1 and type 2 AGNs, perhaps due to different geometrical position of the observers. Type 1 AGN show both broad and narrow lines because we can observe both broad line and narrow line region. Type 2 show only narrow lines because narrow line region is hidden. However, the picture is not so simple. There are interesting intermediate types, like changing look AGNs, switching their spectra, for example, between type 1 and type 2 mode, like NGC 3516 observed recently by late Professor Alla Shapovalova, and Dragana Ilic. Going back to task of Serbian team within LSST, which is actually detection of supermassive binary candidates in LSST upcoming database, we can say that until space-borne gravitational wave observatory LISA is ready to fly, the question is, can we catch photons of compact supermassive binary black holes with LSST? We know that LIGO double black hole mergers are totally photon-free, but here, theoretically, yes, we can catch photons because Bondi accretion rate scales as mass square of the object. Second, in merging galaxies, dynamical disturbances are pushing gas to the center and binary remains as bright as quasar almost up to the merger. Also, binary accretion rate is modulated periodically and may be rendered into periodic signal in the light curves. Technologically, yes, we can catch photons because LSST instrument is fast enough to monitor binary in real time, even during the final stages of the merger. We will catch actually the signals of the binaries dominated by Keplerian motion, which means that the binaries is well decoupled from the environment. For those Keplerian binaries, one of the most effective observational evidence is a periodic signal associated with the Keplerian motion, such as the periodic or quasi-periodic variability of the light emitted by the object. However, to discern periodic variability due to binary from the common variability of AGN is challenging because it relies on long-term monitoring of the candidates and the signal is buried in the stochastic red noise of the IGN. This problem is similar to detection of submarine in the ocean. Both submarine and binary supermassive black hole detections are complex pattern classification problems involving time-varying and mixed environments. Environmental noise causes signal waveform distortion, loss of signal information, and incomplete received signals due to the complexity of the signal propagation medium. Let's continue to LSST binary sample. Here we predict what will be the sample of closed binary supermassive black holes collected by LSST. Based on theoretical assumptions, we can actually estimate the residence time, which is actually the time binary is expected to spend at specific orbital separation. The cadence and length of time series defines the ranges of the periods we can identify across the redshifts. For 10 years of observations, for the total mass of binary of 10 to power 8 solar masses, the range of accessible periods decrease with the redshift due to redshift correction, as expected, and we can see that for smaller ratio of masses of components in binary system, the residence is larger, keeping that pace across redshifts. Although the number density of expected closed binaries is higher for smaller mass ratio of components in the binary system, the peak is at redshift 2 for all cases because there is a general peak distribution of AGNs. And we estimated that sky coverage will be significant across observed magnitudes. Finally, we also predicted the cadences for LSST required to determine periodicity with 13% accuracy using our software. If applied on the Thenia long light curves of AGNs, at redshift 7 for 20% variable object, the cadence would be about 12 days, but for 10% variability, cadence is about 5 to 6 days at redshift 4. The plot shows that expected error across redshifts will be smaller for more variable objects. In order to detect oscillations, we can use different methods like Fourier-based methods, like periodograms, but perhaps they will not work in the case of LSST due to possible sparse light curves. And we need more modern machine learning-based techniques in order to detect periods. LSST will have fast filters alternation, implying possible cadences of few days, and they will be insufficient for application of standard methods. In such situation, we can craft LSST periodicity search flow with incorporated novel machine learning-based methods. One of these tools is also our 2D hybrid method, comprising Gaussian process learning of light curves, which correlates matrices of continuous wavelet transforms of Gaussian modeled light curves. we end up with a map of correlated periodic signals present in both curves. Contrary to periodograms, our method doesn't a priori assume the form of the underlying periodic signal, and the different topologies of our 2D method maps are related to different dynamical regimes of objects, offering new possibility for classification, not only by the geometry, but also on the dynamics. Our method can distinguish different dynamical regimes, and we can actually incorporate them if it passes some checking, which is in the progress. Also, our method can deal with uneven amount of data, as it was the case of famous binary candidate PG13021102, which signal became distorted recently. Sasha Simic and Luka Popovic modeled and explained this distortion as a temperature inversion within the disk. Another interesting case, Markarian 231, a binary candidate with highly unequal mass ratio, about 0.03, with very tight mutual separation of 600 astronomical units, we detected and confirmed actually orbital period of 1.1 year. That is interesting because the majority of small orbital periods have peak about 1.2 year. And we actually have the information desert about the periods of the order of 1 year. With our confirmation of the period of 1.1, we actually support, even though not prove, the intriguing hypothesis that binary supermassive black holes with low mass ratio may be more common than close equal mass supermassive black holes. In this talk, we actually show what is the LSST, what we can expect, and emphasize the importance of joining electromagnetic information with the future gravitational wave observatory data into multi-messenger information, and some possibility which can be done with the LSST. We also show our method, which is now in the process of evaluation. And coalescing binary supermassive black holes are the most powerful sources of gravitational waves in the universe, which makes them a new frontier for upcoming gravitational wave observatories. I would like to thank to the organizers for this great event. It is an honor to be here with you today. I would like to thank the chair, moderators, and thank you audience for the interest in this topic. Also, big thanks to the LSST community and AGN scientific collaboration. Special huge thanks to the AGN scientific collaboration leader, Professor William Brandt, Penn State University, Gordon Richards, Drexel University, Sebastian Henning, Southampton University, Franz Bauer, Pontificia Universidad Católica de Chile. Without their input, this work and presentation wouldn't be possible. Thank you.
Angelika, thank you very much for this very interesting presentation, and we are looking forward to the start of operation of LSST first light next year or 2022 and
operation in 2022.
2022, yes.
Yes.
So now it's time. I see a lot of applause. Is there any question? Comments? Yes, Dragana Ilic.
Hello, everyone. Hello, Angelika. I really have to comment this excellent presentation, Angelika. I was really enjoyed your talk. Thank you very much for.
But we have been working together on this.
I know. But it's always nice to hear how it sounds exciting. I just wanted to ask you a question. So can you comment more about this number of? You said that number of binary supermassive black hole. The last slide, yes, actually that one. Can you comment once again on these predictions that you are you came in your work about the number density of not the number density. You said that they are more common, the binaries which are with
About the length of the period.
Yes, yes.
Yes, you can see actually here the study by Carisi from 2017, where you can see actually the distribution of the observed periods and orbital periods of different, and here is the number of quasars. And what we can see actually here is that the desert, they didn't isolate no one candidate which could have 1 year orbital period. Majority is about 1.2 or below. So actually, it can be the consequence maybe of the observational bias, but also the consequence of the methods applied. Here, what is interesting for the Markarian 231 is actually it has also sparse curve, and there have been great debate about the origin of the oscillations in the light curves of this object, but we detected 1.1 year signal coming close to the threshold to this desert of 1 year. Previous detection was about 1.2. What we expect for the LSST is actually that this desert actually can be populated and to see what is happening here. Interesting here for the Markarian 231 is actually like what I really fast emphasized during the talk, that it is highly unequal binary with a mass ratio about 0.03. So these objects are really, really interesting, and we expect more, larger sample with such objects caught by the LSST.
Yes, thank you very much. I mean, this desert is really interesting to explore, and as Vlada says, we're looking forward to the LSST light curves, and we will see what will come up with this. Thank you very much once again, and see you later.
Thank you. See you. Thank you, Vlada. Thank you.
Thank you, Angelica. I see there are no raised hands. Maybe some comments from the audience. If not, thank you, Angelica. And we are doing the program now. Next speaker is Jelena Petrovic from the Astronomical Observatory. And I think Congress Rental is playing this presentation. So if it is ready, we can start.
Hello, everybody. My name is Jelena Petrovic. I'm working at the Astronomical Observatory in Belgrade. And the title of my presentation is The Evolution of Stellar Interiors in Massive Binary Systems. First, we want to see why a massive binary system is so interesting. They seem to be connected with many interesting phenomena, and a few are listed here on this slide. Number one, Wolf-Rayet stars. That would be this illustration. Wolf-Rayet stars are helium core burning stars that have lost most of their hydrogen envelope. It is assumed now that this hydrogen envelope is lost during mass transfer to the companion star. Then we have 1B or 1C type supernova explosions, which exhibit lack of hydrogen. So this can also be due to some previous interaction in the binary system. Third would be X-ray binaries, where we have a massive giant transferring mass onto a compact object. Accretion is formed around compact object, and there is X-ray emission. Then a binary system seems to also be connected with gamma ray bursts explosions, because there is an idea that fast rotating massive black holes can be actually sites of gamma ray bursts. these fast rotating black holes are called also collapsars. And the newest discovery is that the gravitational waves, emission of gravitational waves, can be connected with compact object mergers of black holes and neutron stars. And this is something that we want to look into. And I am giving here a list of gravitational wave events observed so far by LIGO and Virgo collaborations. Who is interested in more details can also look at this website. Here we have a list of observations, their names, dates when they are published, and masses of progenitor binary systems. The red masses are below 2 solar masses, and this would be double neutron stars. All the rest are double black holes. Now, just to go shortly through the evolution of binary systems. How is this really going? First, we have 2 main sequence stars. The main sequence means they are burning hydrogen in their cores. After a while, the primary will expand enough to start transferring mass to the secondary. This expansion and start of mass transfer can happen during core hydrogen burning. After it, when hydrogen starts burning in envelope already, or even after core helium burning phase. Depending on this, there is classification of mass transfers, case A, B, or C. But there can be also combinations like case A, B, where mass is being transferred during core hydrogen burning, but also afterwards. What happens eventually, the primary will become helium core burning star, so Wolf-Rayet star that we have already mentioned, and the secondary now accreted some extra matter and is more massive than originally. Primary evolves faster because it's a higher mass than the secondary, and it goes through the whole sequence of core burning. So helium, carbon, oxygen, silicon, iron core is formed. We have supernova explosion and a relic, which can be neutron star. He's mentioned neutron star or black hole. Secondary is still main sequence core hydrogen burning star. Afterwards, we can have these X-ray binary configuration that we have mentioned before. If masses are very different, then common envelope is formed. Anyhow, secondary will also go through all sequence of core burning of different elements, also explode as a supernova, and we will have 2 compact objects at the end. This is what is very interesting, because merger of such compact binaries, neutron stars and black holes seem to be connected with emission of gravitational waves. Now, we want to try to model evolution of such systems. We want to see which initial parameters and how to get to final double neutron star or black hole system. And for this, we first have to take into account that initial stellar masses have to be, let's say, about 20 or even more, because there is mass transfer involved in the evolution, and also that the initial mass ratio has to be close to 1. If this is not the case, then mass transfer is not stable, system evolves fast into common envelope, and there can be merger very early in evolution, so we never come to this double compact object configuration. Then we also have to think if it's conservative mass transfer or some matter is lost from the system. Now, from some previous papers that are published, it seems to be that accretion efficiency in such massive system is very low, even about 10%, so this is what we will assume. I'm listing here a few known numerical codes for stellar evolution that were used in the past. Some of them are still used. But now, these models that I'm presenting to you, that I will present to you, are made with this newest numerical code, Models for Experiments in Stellar Astrophysics. Just a short reminder on one of the previous codes, Stern, that was also mentioned on the previous page. This was done with this numerical code. models were made of Wolf-Rayet plus O observed systems, and there we have found that accretion efficiency of only 10% reproduces observations the best. Now, shortly about models for experiments in stellar astrophysics. That's open code, everybody can download it and use it. It's hydrodynamic stellar evolution code, calculates simultaneous evolution of both stellar components in circular orbit. It calculates mass transfer and includes a lot of physics that is listed here. So nuclear reaction library, convection overshooting, semi-convection thermohaline mixing, opacity tables, all kinds of stellar wind prescriptions. Rotation can be included also. Sprout-Taylor dynamo for magnetic fields, mass transfer, accretion efficiency control, calculations of changes in orbital angular momentum, etc., etc. Now, people are already wondering, how can we reproduce this? How can we get those systems, those double compact systems that can be sources of gravitational waves? And this is from a paper by Krutsko and all from 2018, and they were looking which initial primary masses and secondary masses can produce which kind of double compact object. They were taking different metallicity than solar 002, this is Milky Way and some other galaxy here, and you can see here that only starting from 30 solar masses, they did this in population synthesis method. That is, these are models that are done without many details, but you can do really many models very fast. They found that somewhere from 30, you can start from initial masses of around 30 and above, you can start actually forming double black holes, while under that would be neutron stars. And this is more or less the same, as you can see. It's about 30 that it starts being possible to make double black holes. Now, we want to try with MESA and see how does this work and can we produce these kind of systems. So here I'm going to show you a few systems that we have modeled, and I'm starting with one example. Initial masses of 30 and 27 solar masses, mass ratio 0.9, near 1, so we would avoid unstable mass transfer, and initial orbital period of 3 days. Now what we see here, here is a central temperature, and here is mass of a primary star, mass of a secondary star, and orbital period. Mass of primary is starting from 30 solar masses, but due to mass transfer, it rapidly goes down, you can see. And it ends, this primary star ends on only even under 10 solar masses. Secondary, on the other side, accretes a bit, but since accretion efficiency is put only to be 10%, then this is just a small change. Period, orbital period starts from 3, but is going towards and above 25 days. These are convective or so-called Kippenhahn plots that show internal structure evolution. This is the same example. Here the timeline is shown, and here is the mass, and each of these slices would show internal structure of the star at that point. Blue regions are showing where there is nuclear burning. So up to here you can see 20-something solar masses. We have burning, nuclear burning in the star, and this would be enveloped, whereas white, green regions are showing where are convective zones. And then here you can see carbon core is being formed, and later on oxygen core. This is primary star. Here is its total mass that goes from 30 down towards under 10 solar masses. Secondary star in this system is actually first losing mass because of stellar wind, then it gains something due to mass transfer. In interior also we have regions with nuclear burning where core hydrogen burning is happening, and this is convection. due to accretion from the primary, actually size of hydrogen burning core is increasing, and this is so-called rejuvenation. Another example, a bit more massive system, 38 plus 34.2. I'm showing this just for two more features, and this is so-called semi-convection and thermohaline mixing. So this is shown here with red and with yellow. This is what is interesting is this thermohaline mixing, and that is due to accreted matter, and then heavier elements are going slowly down. This is just to show you how these interiors are actually changing with time and due to mass transfer. Now, we have calculated altogether these 6 models. Primary masses from 30 to 40, and we kept initial mass ratio on 0.9 and initial orbital period on 3 days. So this is what we have tried. And here you can see this is again central temperature. This is mass of the primary star in all these systems. You can see here which one is which color. And what you can see for all the systems that due to mass transfer, all these primary stars will lose significant amount of matter. Now, these two systems have been calculated all the way to supernova explosion, to actually formation of iron core. These others didn't come to that yet. This is something we are still working on. But you can see that their final masses are under 10. Mass of the secondary is going down due to stellar wind for each and every of these secondaries. Then it's increasing due to the mass transfer. Oh, sorry. Orbital period evolution is shown here for all systems. You can see here that even though initial masses are in a range from 30 to 40, periods are all starting with 3 days, and orbital period evolution is almost the same for all of them. So here is a little table that is showing actually this situation in Wolf-Rayet plus O phase. So this is initial, and this is Wolf-Rayet size or helium core burning star. And here you can see that the first system will evolve into 8.4, Wolf-Rayet star, second 9.2, 10.7, 11.3, 12.4. This system is showing that stars are expanding really fast one after another and go into contact earlier. So this is something we are still looking into. Periods, as you can see, in the range of 22 to 27 days. In this slide, I'm showing evolution to the formation of iron core in the primary stars. In these two systems, 30 plus 27 solar masses and 32 plus 28.8 solar masses, the evolution is calculated all the way to the formation of iron core. And here on this plot, we can see here central temperature, value, logarithmic scale, and here core mass. Helium core is shown in blue. Then we have here carbon core, oxygen core is green, silicon core is shown in red, and iron core is here in purple. And we can see here the values of core masses are given in this table. Iron core values, mass values at the end are around 1.7, 1.75 solar masses, which means that the primary in these systems will end up as neutron star. So even though it's 30 and above 30 solar masses, we are still not getting their black holes because these primaries lose too much matter during the mass transfer. So altogether, now to summarize, we have shown here detailed evolutionary models of a few closed massive binary systems, mass range between 30 and 40 solar masses for primary stars, and initial orbital period of 3 days, initial mass ratio of 0.9 to avoid contact during the first mass transfer. We kept accretion efficiency very low, 10%, based on our previous paper that were showing models for Wolf-Rayet plus O systems. And actually what we have so far, we start with 2 O-type stars, then they go through KSA mass transfer, going to Wolf-Rayet plus O systems, then primary will eventually go into supernova explosion, and we can estimate already masses of these neutron stars based on iron core masses that we have calculated. However, we still have to finish and work on detailed evolution of a couple of those systems that came to helium and carbon core burning, but iron core has not been formed yet. And then the secondary evolution has to be followed further. What we can see is that the secondary at this point where we stop currently following evolution, that the secondary has helium core of about 10 solar masses, which would indicate iron core mass of also about 2 solar masses, which would indicate that these systems that we have followed here, that we have modeled between 30 and 40 solar masses, would all still lead into double neutron star systems. And the reason that we were doing all of this is because such systems after merger, during merger, could actually produce gravitational waves emission. And something for the future that we still have to look into. Orbital period is calculated with MESA until the first supernova explosion. Further, there are things that cannot be followed in detail, but some estimates come into the story because we have supernova kick after the first supernova explosion. We have common envelope when the primary is already compact object and secondary is giant, which would not actually then be possible to evolve anymore via stable mass transfer. So this is something for the future, and we will be working on this to find what initial systems and what initial parameters can lead to double neutron stars or double black holes that can produce gravitational wave emission. Thank you very much.
Thank you, Jelena, for this presentation. Very interesting. Do we have Jelena?
Yes, I am here. Hello, do you hear me?
Yes.
Hello.
Yes.
Okay, great.
We hear you. I see applauses, but no questions. Do we have a question?
I have a question, Vlado, if I can.
Yes. Please.
Okay, Jelena, thank you very much for a nice talk. It is very interesting, and I have a question in your MESA models. Which is the maximal mass of primary star that you can include?
So far, what I know that masses up to, let's say, about 100 solar masses have been made. Now, there is no real limit. So this is also something we are intending of testing, because as I have shown, you do need quite high initial masses to actually produce double black hole systems. So this is something that we will still indeed look into, but so far I would say about 80 to 100 solar masses.
And if I can, one more question, Vlado.
Sure.
And what is the maximal differences between the masses of the primary and secondary star?
You mean in initial configuration?
Yeah, initial configuration. Some example, if you can consider some smaller stars that can influence to the evolution of a massive star.
Right. So indeed, it has been shown so far that initial masses shouldn't be too different. Or what happens is that mass transfer rate becomes too high. Secondary cannot manage to accrete all that matter. It expands, and then we have contact situation in the binary. So this kind of systems would further go through this so-called common envelope, which is like matter engulfs both of these stars, and then there can be merger or drastic shortening of orbit very early in evolution. So this is also something that is not exactly known, as something that we will look into where exactly is that line, but somewhere 0.8 mass ratio 0.9. This is something that comes from our previous models and also previous models of other authors of really massive stars. So let's say 0.8 and above should be initial configuration or initial mass ratio to avoid this contact early in evolution.
Thank you, Jelena.
Okay, you're welcome.
I see no other questions, so we can thank to the speaker and go with the program. Thank you.
Thank you very much. Bye.
It's my pleasure to introduce and announce next speaker, Alexandra Ciprianovic, from the Fermi National Accelerator Laboratory of the States. So, Alexandra, good morning or good evening or
yeah, it's the middle of the night here, so thanks.
Good.
So I don't know. Okay, let me share my screen. Okay. Can you see the presentation?
Yes.
Okay, thank you. Thank you so much. So for a few people here that don't know me, I see some names that I don't know. I used to work at Department of Astronomy in Belgrade, and now I'm research associate at Fermilab. And thank you for the opportunity to talk about this topic. So I'm going to talk about multi-messenger studies of particle acceleration on large scale, so in galaxy clusters and in accretion shocks. So let's see, a small introduction. So galaxy clusters are largest gravitationally bound objects in the universe. And we can learn about galaxy clusters both from simulations, like what you can see here on your left. So this is an example from a large-scale simulation called Illustris. And we can also learn about galaxy clusters from different observations from different wavelengths and using different observables. So on the bottom right, you can see Coma cluster, a very famous cluster, a large cluster that has over 1,000 galaxies that we observe at different wavelengths. And here are just a few examples like X-rays, visual, and Thermo-Svinyato-Zeldovich. And galaxy clusters are very important objects for various different studies in astrophysics. So you can learn about a galaxy formation and evolution, about cosmology, about dark matter, gravitational lensing and gravity, about the Big Bang and the evolution of the whole universe, basically. But you can also learn about particle acceleration, and that is something that I'm going to focus on today. So again, a few words about the actual particle acceleration in space. So highest energies of particles in space, or cosmic rays, they can reach far above what we can produce in accelerators on Earth, like the one that we have at Fermilab. But so the whole recipe for particle acceleration in space, it's a process called diffusive shock acceleration, but I'm not going to go into details of how that works. What is important is that you have to have three main ingredients, basically. You have to have particles that you want to accelerate, so some kind of a charged particle. You have to have magnetic fields. And finally, you have to have some kind of a shock wave. Unfortunately, those three things can be found in different environments in space and on different scales. So, for example, active galactic nuclei or supernova remnants, or even solar wind termination shock or similar shocks around different stars can produce cosmic rays. And on larger scales, and this is something that I'm interested in, is a process of large-scale gas accretion. So onto galaxies, clusters or large-scale structures can also produce cosmic rays. And cosmic rays are important to study these high energy processes, but again, they are kind of problematic because they are charged particles, so they don't really travel in a straight line towards us. So the apparent source position when we detect a cosmic ray on Earth is definitely not the right position of the origin of that cosmic ray. Fortunately, cosmic rays interact with gas in the objects where they are accelerated, so they produce different things like gamma rays or neutrinos and stuff like that. And those things do travel in a straight line. So by observing these results of the cosmic ray interactions, we can actually learn about the sources that accelerate cosmic rays. So how are these things that we can observe actually produced? So for example, cosmic ray proton can collide with a gas proton, so proton of lower energy, and they produce neutral and charged pions. These particles are not stable, they will decay very quickly, and the products of these decays we can observe. So neutral pions decay into 2 gamma rays, we can observe gamma rays, and charged pions, we can decay into neutrinos, antineutrinos, and muons. Muons again also decay, producing electrons and positrons that gyrate around the magnetic field lines, producing proton radiation, which is in radio waves. So we can observe that with a radio telescope, and of course neutrinos can be observed with the neutrino telescope. So the next thing is what can background observations actually tell us about galaxy clusters? So here you can see several different all-sky images in different wavelengths. And as you can see, our galactic disk is the brightest source. But even if you remove the galactic disk and all the other bright point sources, you still end up with the background that is basically a sum up of all different populations of unresolved sources. So galaxy clusters are one of those unresolved sources that contribute to the background. So studying background can actually tell us about the population, this population of objects, about galaxy clusters, and about particle acceleration in them. So the next part of my talk is actually going to be divided into 2 parts. One where I will show an example of how we can connect gamma ray observations with neutrino observations, and one where I will talk about radio waves and Thermo-Nev-Zeldovich effect. So we are going to link observations of the backgrounds. So for example, plots here on the right, spectrums of the backgrounds extracted from these images. So something that looks like the top left plot. And finally, we can use also observations of particular objects. So for example, you have a gamma ray ring observed around the Coma cluster, but we will use other different observations of particular galaxy clusters. Okay, so let's start with gamma rays and neutrinos. If we want to understand the possible contribution of unresolved sources, we have to understand that we are summing up all of the sources that ever existed, basically. So we have to think how the number density of these objects evolved over time, and also how different things that that result in the observables evolve over cosmic time. So in order to produce the possible contribution of unresolved galaxy clusters, we have to write an equation like this one that you see on the screen. And I've circled out different parts of the equation so that we can go through them really quickly. So there are different parts of this equation that are important. Cosmology is one of that. So you have to include the cosmological parameters. You have to include cosmic accretion rate, because we're studying accretion of gas on large-scale structures and in galaxy clusters, and that evolves over time. You have to include the evolution of gas fraction in these clusters, because the amount of gas means a different amount of targets for the cosmic rays to collide with. We have to add gamma ray spectrum, and we have to normalize our models to a typical galaxy cluster. So on the bottom, for example, you can see models of how cosmic accretion rate evolves over time. So for example, these curves are actually the red part of the equation. So we want to use this, and also we want to combine this with neutrino observations by IceCube and connect neutrino background that was detected to normalize our models. So we have to assume 2 things. First, we have to assume that the evolution of cosmic accretion rate directly translates into amount of cosmic rays that you can produce, and that the resulting gamma rays, neutrinos, radio waves, or whatever else we want to observe directly also translates to the amount of cosmic rays. And in particular for the gamma rays, we have to assume that most of the gamma rays that we observe are from neutral pion decay. If that is true, then we know the shape of the spectrum, which will be a broken power law, like you can see here on the bottom left. Okay, so now how can we connect gamma rays and neutrinos? Well, we can connect them very easily because from experiments we know that neutral and charged pions are produced in the same order. So basically you have this very simple equation on the top that links gamma rays and neutrinos, and it only depends on this parameter alpha, which is the spectral index of the spectrum of cosmic rays. So in case of very strong shocks, alpha will be 2, and in that case, we will have 2 times more neutrinos than gamma rays. So it's actually quite easy to link gamma rays and neutrinos if you assume that they are from the same source. So here are some results related to this study. So in case we assume that, for example, the entire neutrino background was produced with from these gamma rays from galaxy clusters. The neutrino background is the gray shaded area. We can actually produce from that big equation that I showed this red line here that you can see. And the gamma ray background is given with the data points. So these are observed with the Fermilab telescope. And as you can see, we can account for only 12% of the gamma ray background in case of strong shocks. But of course, there are additional contributors like normal galaxies or blazars. And when we sum up all of those things, we get the blue line, and we get a lot more contribution, of course. But of course, there are still a lot of unknown things. So for example, there are papers claiming that only 20% of the neutrinos, for example, can come from galaxy clusters. If that is true, then of course, our contribution has to be even lower. Okay, so let's go to radio and thermal Srinivas-Aldovich. So in radio waves, you also have the background radiation, and it is actually seen as additional signal on top of the cosmic microwave background. So on this plot, the cosmic microwave background level of 2.7 kelvins would be the horizontal dashed line. And what you can see on the left, this extra signal, that is the cosmic radio background. And unfortunately, as with gamma ray background, we don't really understand it completely. And all of the sources that we think can contribute to the background can account for, until now, only around 67% of the background. So a third of it, basically at 1.4 gigahertz, for example, we don't really know what it's made of. So we can use same models like with the gamma rays with just slight changes to see how much can galaxy clusters account for this in this cosmic radio background. So there are 2 ways to produce radio waves. There are hadronic models, like the models that I already were talking about with charged pion decay, where you produce electrons that will produce the synchrotron radiation that you observe. And the other models where you already have some lower energy electrons that are reaccelerated to cosmic ray energies through turbulences. But for now, we'll concentrate on the hadronic models so that we still keep talking with about the same process. Okay, so here on the left, you see a galaxy cluster, A2319, observed in radio waves with VLA and with Green Bank telescope. And in the middle, you can see the power law spectrum that the 2 observations produce for this galaxy cluster. But we are going to link that with observations of the thermal Srinivas-Aldovich effect for the same galaxy cluster that you can see on the right. This is very important observation. This is actually the first cluster that was observed with this effect. And thermal Srinivas-Aldovich effect is upscattering of the lower energy CMB photons by the high energy electrons in the galaxy cluster. And so you can see this galaxy cluster with this effect as like an additional bright spot. And this is important because this can actually tell you the position of the accretion shock and the accretion rate of that galaxy cluster. And this was actually calculated for this particular cluster, as you can see on the bottom right. And that we can use to normalize our models so that we can link radio and thermal Srinivas-Aldovich. So here are some preliminary results related to that study. So the black line here is the radio background, and the data points are the observations. And the 2 colored lines actually give you the possible contribution of unresolved galaxy clusters to the radio background. What you can see here, for example, for 1.4 gigahertz, which is an important frequency where a lot of measurements were done, we can account for very little, actually less than around 1% of the background. But on lower frequencies, we can account for much more. So again, as with gamma rays, there are still a lot of unknown things here. And these are just some first preliminary studies about the possible contribution of galaxy clusters through hadronic mechanism of production of electrons. And finally, as you can see from these two examples, galaxy clusters are really important for the studies of highest energies in space and particle acceleration in space. But in order to understand really the whole process, we really need to leverage multi-messenger studies like in these examples. And the only problem is that we still need a lot more data and a lot more better observations, especially of particular galaxy clusters in these wavelengths, because, for example, Thermosunai-Zeldovich, but also gamma rays are actually very problematic. So galaxy clusters are very hard to detect. So the future of surveys and future big telescopes are really promising because they will provide better data and we will be able to connect the dots better and actually learn about particle acceleration in accretion shocks. Thank you so much.
Thank you, Alexandra, for this very interesting and beautiful presentation. I'm not expert in this field. I have one general question. What are are you facing some problems in models, and what are the weak points of this investigation or something like that?
Oh, well, there are different things that we have to assume, unfortunately, in these models. So there are a lot of things that we can do better, and we will in the future. But for example, one problem is that you have to assume that a galaxy cluster, for example, that you're normalizing your models to is a typical cluster, and we cannot be completely sure that this is true. So this is one problem. And then you have to, of course, assume that, for example, the spectral shape of all other galaxy clusters that are mostly contributing to the background is similar like to the cluster that you can observe and that you're using for your normalization. And that is, of course, at least to some extent, not going to be completely true. So a lot more details to actually get the end contribution. So this is just one example, but unfortunately, many other things were done by either semi-analytically or in theory or based on just a few observations from particular objects. So a lot of things I think we can improve, but for that we will need a lot more observations.
Thank you very much. Is there any other questions, comments from the audience? I see a lot of applause, but no questions. We have 1 or 2 minutes, so if not, we can close this morning session. This is the last lecture, and thank you very much.